Let's wait for a few more minutes in case anyone else is joining. So let's get started. So hi everyone, I'm Ayush Kumar Tyagi. I'm PhD student at IIT Delhi. I work in medical imaging with a combination of computer vision and deep learning. And yeah, so I work primarily in histopathology images. We have collaboration with AIMS, and there are some diseases or like there are some problems which we are trying to automate using deep learning methods. So for today's session, we will be primarily looking into like PyTorch, how are you basically going to code this neural network. We will see what are the best practices for using PyTorch, and we will try to solve some sample problems as well. And parallelly, we will also like look into maybe some few questions which might be relevant to the topic and can be like asked in the exams or like so. So let's get started with few of the questions. Yeah. I hope you have seen the lecture slides, videos which were released, and I think because that is a prerequisite, and we are building basically on top of that. And but in case there is some doubt, feel free to ask. I can actually go over it again from theoretical perspective as well, right? Yeah. So let us see, so the question is, consider a simple perceptron f such that f is R4 to R, which uses a 10H function as an activation function. The input vector is x and corresponding weight vector is already given, that is w. Compute the derivative of 10H of z, where z is basically a linear combination of w and x. So what it's given to us, and we are basically ignoring the biased, and we know that z is basically a combination of x and w, and what is required from us is that 10H of z is basically uh, like we want to compute this and then compute the derivative of this entity, right? So let's see, like for the theoretical perspective, what should be the derivative of 10H? Any ideas? 10 h of z is basically e to the power z to the power minus z. I guess so. And if you basically try to derivate it, I think it looks like sec square, and that is basically equal to 1 minus 10h square z. So the derivative comes out to be 1 minus 10h square z. And in so like we want to compute what should be the value of this entity, right? So for before that we should start with computing what is z. Z is basically x, or maybe a w transpose photon you can actually write. X into w transpose. So it is what is happening here is we are just saying 0.5, 0.7, 0.9 and 0.3, and then we have w which is 0.6, 1.5 minus 0.4 and 0.8, right? And if you compute it, it should come out to be like it will come out to be minus 0.87, right? And if you compute the value of 10h square z, that is 10h square of minus 0.87, it turns out to be close to 0.49, right? But we are required to compute the derivative of 10h. So what we do is like will be 1 minus 0.49, which turns out approximately 0.5086, right? So the takeaway is basically to identify that what is the derivative of 10h, right? And then everything boils down to filling in the values, right? So next is, which of the following statement is true regarding the impact of dropout on the network performance and the final learn weight? So dropout is basically what happens in whenever we are training a neural network and we are saying that like it is kind of overfitting. What we do is we try to drop few of the neurons during the training in a in a random way, and in the whole process what you are trying to achieve is one is that like any dependency on of neuron on previous neuron layer. Suppose this there are these neurons, and what neural network has identified, it has identified a shortcut basically. So it says that like whenever this neuron is activated, uh, this neuron get activated and the output is y is equal to suppose 1. So like in a more abstract way, suppose there is a dog classification problem, and suppose what your neural network is looking is it is basically looking at maybe the ears of the dog, right? So whenever it find ear of the dog, the one neuron get activated, and then it simply bypass other features and become too dependent on this feature, right? And whenever you find a ear, it basically says that y is equal to 1, right? So it's a dog. But there are other species which might have the similar structure of the ears. So those features the model is not learning, right? So what you want is like during training you want to drop this the neuron, so that like the next neurons should uh, we can actually compel other neurons to look into other features as well, maybe the nose, right? Or maybe the feet or kind of texture of the fur, right? So these features also come into play, right? So this uh, dropout is basically breaking this kind of shortcuts which a neural network might have learned. So this is also a form of a data augmentation also, because what we are essentially doing is, like at every training, we are perturbing the features. So the model is actually looking into new type of features every iteration. uh, and there is one view where dropout is also called as the ensembling process, where because every time we are training almost a new network, because we are kind of randomly dropping the weights, and at the end what you are doing is we're kind of ensembling between different networks to get a final network. So there are different perspectives of looking into the dropout, but one of the most sought after is like to avoid overfitting, learn more robust features. So that is the story of dropout. Any questions? Like just let me know. Uh, Feel free to interrupt. Right. So, which of the following statement is true regarding the impact of dropout on the neural network? So, dropout during training cause network to overfit because it randomly drop neurons, making the model too simple. Not true. During training, with dropout, the model adjusts the activation levels so that the output remain consistent between dropouts when dropout is not applied and it is applied. That is true, because like if there was input coming from four different type of neurons, when you drop, like now the signal is basically coming from only two of them, then you need to actually adjust your activation scale, so that like you can actually say that if even these features are important. And like suppose you say that you are kind of dropping out ears and skin, like fur texture, but nose is important. So if one of the neurons is basically getting triggered with nose of the dog, then you should actually pass that information to the further layer, so that activation function need to be adjusted, right? So this is true. Dropout during training lead to smaller final model, as some connections are permanently removed. So this is false. No connection is permanently removed. These are basically dropped during training, right? And these are dropped randomly. The final output during training is multiplied by the dropout rate to maintain the expected output when dropout is not applied. Uh, is when dropout is not applied during training. This is not true. Only it's partially true. So, like what you do is like you actually find out what is the expected value of a neuron to be dropped, and you scale your output, output of the intermediate layers with that factor, right? So the correct answer is only B. So it's given. Uh, Whenever there is another way of doing the regularization, there are different type of regularization methods as well. So L1 is one of them, L2 is one of them. So what we are trying to do here in L2 regularization is we're trying to reduce the complexity of the model. So in both the cases, L1 and L2, what people are trying to do, we're trying to reduce the complexity of the model. That means, like suppose we have maybe uh, thousand neurons for a very simple problem, but not model maybe the data is not that complex, so you don't need so much of computation capacity. So what happens is like it starts overfitting very quickly. So your training loss basically reduce like very fast, and your validation basically starts to increase. So what you do here is like you are overfitting on the training data. So one way of avoiding overfitting is to reduce the complexity of the model. And how do you reduce the complexity? So one way is basically to you manually reduce the number of layers. The other way is to you switch off few of the neurons. And regularization methods are one of does the same thing for you. So what it does is it try to make the your weights of your network uh, small. So when your weight of your network is either zero or very small, then you're kind of reducing the impact of each neuron, right? So there can be many neurons which are zero. So essentially, you're training a low complexity model. So that's what L1 and L2 does. So let's see what the question asks from us. I hope it is clear, right? And if you guys have any doubt, let me know. So batch normalization cannot be used together with L1, L2 to improve the robustness and generalization of the model. That's not true, right? It can be used. L1 regularization can lead to sparse weight matrix, which means there can be weight can be zero. This is true. So if you look at what does the contour look like, what does the contour look like? So for L1, contour looks like this, and this is suppose your loss space, right? uh, and it either intersect with, maybe suppose there are w1 on w2 this side, so it either intersect at this point or maybe this point. So and at this point you have a value for w1, but w2 is basically 0, right? And similarly at this point you'll have value for w1 is 0 and w2 might have some value, right? So there are two parameters, and we are kind of making, whenever there's an intersection happening here, we are kind of making one of them as 0. So there is effectively one parameter like which we are using, right? So what is happening here is in L1 regularization, it basically leads to sparse matrices, right? And due to which you kind of reduce your model complexity. So this is true. And batch normalization normalizes the input of each layer by subtracting batch mean and dividing by batch standard deviation. It slows down the training. uh, I don't think so. When using batch normalization, it is necessary to disable it using inference phase. That this is true. So I'll just give you a quick uh, detour of what is batch normalization. So for batch normalization, what you do is, like, for a batch, you compute the mean, and you compute the standard deviation of that like variance of that batch, and you rescale your like data with subtracting that mean and the standard deviation. So what happen is, basically, suppose there's something called as a covariate shift. So like you have trained your data on, suppose, this type of data distribution, but whenever there might be some cases, maybe maybe due to the from which camera the image is taken, maybe because the surrounding where these images are taken, maybe the lighting condition, there can be a shift of features, right? So what batch normalization does is, like, it brings everything into the uniform scale. So it brings everything to this scale, so uh, to mitigate this shift, right? So that's why you do subtract with the mean and divide by the standard deviation, and then you rescale everything back to original space using gamma and beta, right? So maybe this was the original space, right? Because if you are scaling everything into one space, and your activation functions are actually operating in the different level, you don't want to mess up that. So you normalize everything and then scale back to the original space, right? And so this happens during training phase, right? And during testing phase, what people generally do is what they do is like they save the overall mean and standard deviation of maybe the validation data, and use that validation, those values, to basically scale your test samples, right? So so using when using batch normalizer, it is essentially disabled during uh, like uh, inference phase. That is basically you kind of pre-compute all the values of mean and standard deviation. You're not learning anything, so only you're basically rescaling everything into like a particular value for x and y. So suppose for the case you have given RMS prop, and what is required is like you want to update what should be the next value of the theta. So there are in this question most of the values are given. You simply just need to feed in the values and you will get the next update. So there are two part. One is basically the gradient accumulation part. So there is I guess there is a decay part where you are basically taking into account previous gradient as well as the new gradient, and some sort of a weighted average you're taking, and then using this to basically see how much the current gradient actually affect the next step. So I think the whole thing is like you need to understand the formula and then just feed in the values. So next is basically the gradient descent, but like in different forms. So suppose there are multiple type of gradient descent. So there is one batched gradient descent where you try to feed in whole batch into the memory and compute the gradient for that, but that basically lead to inefficient use of the memories, because feeding whole batch into your GPU is not feasible, and in most of the cases is basically impractical. So next is basically stochastic gradient descent often leads to noisy path toward convergence, but also helps in escaping the local minima more effectively. So what happen is stochastic gradient descent. So this is what stochastic gradient descent looks like. So what is happening? We are kind of updating the weights with respect to each sample we are seeing. So you see, you take a one data sample, you compute the loss with respect to that, and then with corresponding to that loss you try to update the weights, right? So it is more noisy because you are kind of updating the weights for each instance, but in case of local minimas it doesn't it kind of escapes out of that. Similarly, there's something called as a mini batch gradient descent, which is using mini batch size in mini batch gradient descent generally increase the variance of um, parameters update. So it's so the smaller is your mini batch for this mini batch gradient descent, closer it is to uh, stochastic gradient descent, right? And the higher is the batch size, it more closer it is to batch gradient descent. So so the mini batch gradient descent is some sort of a mix between stochastic gradient descent and a batch gradient descent. So people generally try to optimize it, higher the batch size better it is. So suppose you have uh, like uh, you are keeping batch size of 8 for 500 cross 500 images, and you have a GPU capacity of maybe 16 GB GPU, and it with batch size 8 it is able to fill out the whole GPU, then I think you are making optimal choices for training. However, if you have a GPU capacity of 64 and you are just using only the partial GPU, then I think you are just a minute, you're kind of underutilizing the resources. So you might want to boost up the batch size to maybe 16 and 32. Right. There is a hand raise. So you can actually basically unmute and ask.
Sir,
Madhuban.
can you explain the difference between stochastic gradient descent and mini batch gradient descent?
So what is happening here is in stochastic gradient descent, we are kind of updating the value of theta for each instance. So like you see sample 1 x1 and you compute the output corresponding to that, and then you compute loss, right? And then using this loss only you update the your parameters theta. Whereas in mini batch gradient descent, what you're doing is like you check for like x1 to x8, right? So this is your batch, right? And then you compute a loss corresponding to that. You take a mean value of loss, mod of maybe like divide by 8 your whole loss I1 to I8 minus predicted values of y to 1 to 8, right? And then use this loss to basically update your parameters. So now the signal we are sending for in case of mini batch here it's more uh, like with it's less noisy, whereas when you're updating with respect to each sample it's becomes slightly noisy, right? So that is the difference between the stochastic gradient. Is it clear or?
Yes, sir, it's clear. Thank
Okay,
you.
great. So like recently I think in one of the conferences, so there was one paper called as a mix up augmentation, and this is also this is also augmentation technique, right? So this is called as a mix up augmentation. So what type of augmentation we have seen? So it can be a rotation based augmentation, where you rotate image 90 degree, 180 degree, 270, horizontal flip, vertical flip, those kind of augmentations are there. Then there is a brightness or the contrast adjustment, right? So you change the intensity of few of the colors, maybe change sharpen on more edges more, right? So those kind of augmentations are in the field of comes in the space of brightness and the contrast adjustment, right? And then uh, you can do swapping, or uh, maybe shifting operations, uh, maybe shifting operation, like, right, suppose you have an image and you shift it to right, so this becomes actually empty and your image basically starts from here. And shifting basically and cropping, you so you have this image, you basically crop the central portion and use rescale it to your original image size and use this image. So now uh, like you want the model to basically focus more on the center of the image, and like rather than looking at the out like the outskirts. So what happened in some of the cases, what people have identified, suppose there was a husky which was present, um, right? I don't know, right? So there was some dog, and there was in most of the cases there was snow around the dog, right? Because the Siberian huskies are like generally native to what do you say, uh, the cold environment, right? So what people have identified that instead of looking at the feature of husky, the models were identifying these huskies based on the surrounding, right? So similarly then like camels are native to deserts, so if the model has correlated that camel is a native to desert, so whenever they see a desert in the like image, the model become biased toward camel, right? So people don't want these kind of correlation between uh, like images, right? So suppose you see a camel walking on the maybe in Delhi streets, so you don't want the model says that like okay, so there should not be any camel because camels are correlated with the desert. It should be it can be some other animal. They say model start predicting it as a cow. So those kind of correlations you don't want model to learn. So that's why people actually do this kind of augmentation, and the crop center crop and random crop, those kind of augmentations actually help in that sense, right? So extending the same augmentation space, people has identified that you can actually mix between two images. So suppose there is image 1 and image 1 and image 2. So the final image I mix can be a combination of both images. So how do you mix it? So my mix is basically lambda times uh, I1 plus 1 minus lambda times I2. And similarly your labels for labels can be lambda time y1 plus 1 minus lambda time y2. So this is mix up augmentation, right? So uh, so what happen is like if you see, we can actually go to problem later, but understanding is important. So there is, so this is suppose the data distribution where different classes are there. So maybe this uh, this is a cat class and this is a dog class, right? And if you do uh, whatever augmentation we have discussed, rotation like slightly, and maybe what do you say, cropping and all those things, you are basically making some samples in this space near, very near to whatever the original samples are, right? What mixup does is it creates sample between uh, two type of images. So suppose this is cat image, this is dog image, and when you're trying to interpolate between these two, I'm creating some a new sample here. Or maybe when I'm trying to interpolate between these 2 points, I'm creating a new sample here. That is closer to the decision boundary, right? So what is happening here now, because I have introduced the sample into a model, so model has a better decision boundary now. It may be something like this, right? So that's why this it actually helps in overall improvement in the performance. So as far as the question is concerned, so you have two features. You have x1, you have x2, and what you want, we want to compute what is x mix and what should be the corresponding label for that is y mix. So what you can simply do is you can take lambda time x1 plus 1 minus lambda time x2. Similarly, y is lambda time y1, 1 minus lambda time y2. So I think you can actually work it out. So I'll just show for one like this first instance. So lambda here is zero point 0.3, so 0.3 times 0.2 plus 0.7, that is 1 minus lambda, times 0.8, and it looks like 0.62. Sorry, so the final is 0.62. And similarly, when you compute for y, so y is basically 0.3 times 1 plus 1 minus 0.3 times 0, right? And y1 is 1 0, y2 is 0 1, so y become 0.3 because this is 0, right? So how do you assign a label to it? So what you say is, if it is less than a particular value, it is class 1. If it is greater than 0.5, then it belongs to the other class. So that's how you uh, label it, right? Any doubt here? I think we should take a moment and like see if this is understandable. I mean, let me know any doubt, right? I mean, even if you feel that it's a stupid doubt, just ask it. Like maybe other people are also thinking that. Okay, then I think we should move to coding part actually. I hope you can see my screen.
Yes, sir.
Great. So, let me just change the runtime before. So, what I'm using Google Colab as the platform. This, what you can do is like if you uh, share this tab. Suppose this is my Google Drive. What you do is like just go to this new uh, and just click on this Google Collaboratory. It will open a notebook for you, and you can actually upload whatever data you want, or maybe uh, download from internet, and maybe use your data which is there in the drive to do all the processing. So it already it gives you a good platform to get started with the thing, even if you don't have GPU at your system. It There is one good thing about it. If you go to runtime, change runtime, there are hardware accelerators. These are basically GPU. So there is one premium version for this, like I think it's 200 rupees per month, but you can get access to higher end GPUs as well. So I think whenever you're trying to train any model, I would say just try on either on Google Colab or Kaggle. So Kaggle actually also is basically a platform where people host competitions, and there these are basically priced competitions. So let me just see if so so these are the competitions people have posted. So maybe how it is, like it's look like $100 million competition, and this also provides you an opportunity to use GPUs. So you can like open a notebook here as well, and it gives you 40 hour per week of GPU. So I think whenever if you're starting deep learning, I guess these are the two platforms which basically freely gives you GPU, and so I would say make best use of them. So what we are going to do here is like we're trying to get familiarized with PyTorch. We'll try to see what what are the functions which we need to take care of. We will try to create our first perceptron model where we'll try to solve one of the problems using neural network. So let's get started. So all the libraries you can I think in this case all the libraries are already installed. Torch is already installed in Google Colab. In I guess Kaggle also it is already installed. You simply need to import Torch, right? And like all the necessary modules which are required you can actually import using from Torch import like this is .nn is basically neural network. um, so Torch Vision has predefined data sets like MNIST or some flower data set is there. Those predefined data sets, suppose you don't want to use your own data, just use all already predefined. Data loader is basically how do you structure the data and before feeding it to the model. So we will talk about them, but let's get started first with the basics. So whatever operations we are doing here, these operations can be done in the NumPy, but what PyTorch is basically optimized for GPUs. So and in GPUs we can actually process multiple operations parallelly, and it becomes very fast. So any code which you are running on the CPU is basically, if it is taking 100 seconds, on GPU it basically takes close to 10 seconds. So people are, so that's why there is a race to get more and more GPUs, right? So suppose you want to create a tensor. In NumPy we were creating arrays. In PyTorch we create tensors. So tensors are the one which basically hold the data for us. So you can have tensors from list. You can actually create tensor from tuples. You similar to suppose you have C, which is you're creating tensor from NumPy array. So np.1 basically create a 2 by 3 2 rows and 3 column array, and if you pass this C to tensor torch.tensor, it creates a similar dimension array, but it's a tensor now. So you, for what is a property of a tensor, you can basically push the tensor to a GPU, right? So if you run it, it will basically create multiple type of tensors, right? So it just created a tensor from list, tuple, from a NumPy as well. So if you want to create just initialize tensors with some structure, you can use torch.1 5,3, where you have 5 rows and 3 column, and it will fill all the values with 1. So torch.1 basically fills creates a 5 cross 3 tensor with all the values will be 1. Similarly, you can have torch.zeros and all the values will be 0. You can actually create dot empty, and it will basically create all the values which are very close to 0 or very small values will be there. Similarly, you can actually create randomly as well, right? Torch dot rand 1 comma 3 basically creates 1 comma 3 array, so 1 row and 3 columns, and it basically samples from normal distribution. So any values have equal probability. There is torch.rand n, where you sample from normal distribution, right? So your the initialization of the weight looks like a sample from a normal distribution which is centered around maybe 0 or like have some mean, right? Similarly, you have torch.0 like a. So you have already predefined tensor, and you want to create another tensor which looks like a. So what you do is like torch.0 like zeros like a, right? So the dimension will be similar to a, but the values will be 0, right? Here you can see. So d is equal to torch.rand like c. right? So uh, it is basically creating random values with the shape that is equivalent to C. Um, so one thing which becomes very crucial is whenever there's something called as the seed in uh, your initialization. So whenever there is a randomness associated, you want to minimize that randomness. So whenever I want to initialize things randomly, but I don't want that randomness affect my overall performance, because there are some newer version of the models like diffusion model, or which are very dependent on what type of randomness you initialize them. So you want to fix these seeds. So tosh.manual seed, random.seed, np.random seed, these seed is basically you define it to a particular value. Now all the randomness will be associated with that seed only, right? Let me just show you. uh, So what we are doing here is I'm computing tosh dot. I'm basically creating a tensor with random values, and the dimension is one row and three columns, right? So let us see what it does. So the values are 0.49, 0.76, 0.08, right? So when like how many times, like even if I like run it 100 times, values will be same, 0.49, 0.76, 0.08, right? So although it is sampling from a like uniform distribution, but every time it samples same value, right? So but if I make seed to false, right, you'll see that like it will start sampling different values, and you don't want, in some, like in some application you don't want that. So also, in order to have a reproducibility of your results, suppose you have said that like my model produced like 82% of the accuracy. So in order to ensure that like every time you train your model it produce 82% of the accuracy, you need to ensure that your seeds are set to a particular value, so that like you are initializing all your weights with random with the same random values. Makes sense, right? Great. So similar to NumPy, you can actually create like a tensor with like certain values. You can actually create certain patterns. Like suppose you want to create a tensor with values from 0 to 9. What you say is tosh.arrange, right? From 0 to 10 with a step size of 1, right? And it creates. Similarly, like the counterpart in NumPy is np.arrange. You can have tosh.line space, and you also have a like same value in tosh np.line space, which creates value between 0 to 5 with steps 11, like so that means that it creates 11 values. uh, yeah, so let's get started with the operations of on these tensors. So suppose there are four tensors. We have initialized a, b, c, d. A is initialized with 1, b is random values, c and d are empty tensor. So what I can do is tosh dot add values from a and b and output into c, right? This is one way of writing it, and I can actually assign, like use the assignment operator as well. So tosh dot add a comma b and then assign it to c, like c is equal to tosh dot add a comma b. That also you can do. So tosh dot multiply also you can use bit a and b and assign value to d. So if you see, these are the values which are assigned. Similarly, you can do arithmetic operations as well. A plus x plus y. So x and y are the two like tensors, and what you can do is like simply use plus operator, minus operator, multiplication, division. This is power operator, and you can get the output in the same form a tensor only. So x power y, so what is happening is like 4 to the power of 3, so it should get 64. So what, let's see, like suppose you have a x, you have you initialized a 10 tosh dot ran 3 cross 3, uh, so it's a 3 cross 3 tensor you have initialized. So what you want, you can actually compute the sum of all the values. So if you say x dot sum, it will compute sum of all the values. If you want to compute sum of all the columns or maybe all the rows, what you do is x dot sum, x is 0, it sums all the values for a column, so like this. So this should come out to be 1.10, right? This will come out to be 1.13. So column wise sum, for computing column wise sum, you say like sum x of x is equal to 0, and for row wise sum you say x is equal to 1. Similarly, you can compute mean as well. So you can compute the mean of whole tensor, column wise mean and the row wise mean. I hope it is making sense. Right, so suppose you have a matrix, you're doing some metric addition and multiplication operation. So what you do is, like suppose you have matrix 2 4 5 7, and you have another matrix 1 2 2 3, and you're adding it with 10 10 12 1. What you do is, like, you simply do a multiply b plus a3. So you assign these values to a1 a2 a3, and this basically returns you the overall output. So what is happening here is you are kind of doing the matrix multiplication. 2 into 1, 4 into 2 is 10 at first place, and then you are adding 10 into it, so the first value should be 20, right? So that's how you do the matrix operation. Similarly, you can actually compute the dot product as well. So a dot b, so b is equal to 357, and you're computing the dot product with 248. So what in dot product, what you do, you take the sum of all the individual element wise products, and it should come out to be 82. So let us see, 3 into 2 6, 20 plus 56, it should come out to be 82. So in now let's look into how we are like going to manipulate the tensors. So like suppose you have a tensor, you created a tensor x that is tosh dot arrange uh, 0 to 10. So you have now values from 0 to 9, right? So suppose you want to access the last element of the tensor. So you, what do you say, x bracket minus 1. So minus 1 is basically the last entity. Suppose you want to assign, like check for the values between 1 to 3. So what you say, 1 colon 2 2 3, right? So it basically like look for these values 1 and 2. So minus 2 is basically, so this is till minus 2, so it will print all the values till minus 2, so second last entry, excluding second last entry, right? So it prints all the value. Similarly, this tensor need not to be 2 dimension, 3 dimension, 4 dimension. There can be 5 dimensional tensors as well. So suppose you're assigning a random values to tensor with different dimensions. Like it's basically this is a 5 dimensional tensor. So at, if you say x0 dot shape, it will be 2 4 3 4. 2 3 4 5 like should be the shape, right? So you have one column, like one row, then you have for each row you have two columns, for each column you have three different z's, and for each z you have other values. So it's a 5 dimensional tensor, but like you can access using slicing operation. So just check for x0, and then what do you say, x0 of 0 will take you to the third, fourth and fifth dimension, and then if you say x0 0 0, then it takes you to the fourth and fifth dimension. Similarly, what you can do is, like, suppose you have z is equal to toss dot arrange like values from 12, and what you do, you can actually use reshape operator, which can reshape value into your type of metric. So you can, since there are 12 values, you can reshape it into maybe 6 comma 2, 2 comma 6, 3 comma 4, 4 comma 3 type of like uh, like tensors. And it becomes very useful actually whenever you're like operating uh, with these tensors. You want to reshape them into particular type of uh, particular dimension to fit your case, so that actually become very handy. So if you want it from 2D to 1D, so what you simply do is like z dot flatten, and it become again become the same way, like the way you created it. Similarly, if you want to reshape it back, you can actually reshape it in a 3 cross 4 or 4 cross 3 uh, like tensor. So this actually is something which is very frustrating, by the way. This squeezing tensor. So what happens is, like, suppose you have a tensor which is 1 comma 10. So if you check for the shape, it will say 1 comma 10, and if you try to assign like check what is the value of x0, it will not give you the 0th element of the tensor. So essentially it is a like row tensor only. You have one row and 10 columns. So x0, we were thinking, we sometimes think that like it will give me a 0th element, but it doesn't work that way. So what it does is it will give you the whole 0th row, right? So if you want to like get rid of that, what you do is like x dot squeeze 0. Now you check x dot shape, it becomes the shape of the tensor become 10. And now if you say that, like, if I want to access the 0th element, it will give you the 0th element now, right? So see, and how do you do it? You basically use squeeze or unsqueeze operation. So suppose you have like whenever you're training a model, you are basically inferencing. Suppose you are inferencing a single image, your image dimension become 500 cross 500 cross 3, right? And if you want to pass it to a model, it expects everything into a form of a batch, right? So batch dimension is batch size cross image size, right? So suppose the batch size is 8, so your input tensor to a architecture or a neural network should be 8 cross 500 cross 500 cross 3. But at inference time you have only one image. So and the image dimension become 500 cross 500 cross 3. So you might want to add additional dimension at start, so that is 1 comma 500 cross 500 cross 3. So in order to do that, you can actually use unsqueeze. So unsqueeze actually add another dimension at basically whatever the location you specify. Suppose in our case we want at the 0th place, we say unsqueeze 0, and it will make our tensor 1 comma 500 cross 500 cross 3. Similarly, there is one more like interesting aspect which is become very like useful, is basically the channel perturbation. So like there are different architectures which perceive channels in the different way. So the PyTorch basically perceive in a channel first like manner, where like it is instead of 500, suppose you just load an image, just check for the its dimension, it will show you it's 500 cross 500 cross 3. But what PyTorch expects is it is 3 like 3 cross 500 cross 500. So your number of channel is at the starting point, right? So suppose, and you did the permutation, you feed the model, and you trained your architecture. So like at the inference time, like whenever you have a new image, you click a new image, internally what you're supposed to you do again convert you need to convert it into channel first uh, like way and before feeding it to the output. So even uh, what do you say in maybe in the segmentation problem, whenever you're kind of predicting anything, like it will basically return it in the similar manner, and you need to do the perturbation so that like the output become in your proper visualization based whatever the other libraries take it. So yeah, so suppose you have a tensor uh, with the values 3 comma 48 comma 64. You can actually use x dot permute function, which like it can actually permute the channels. So what you do is like the first at first index you will take the first value, that is this one. At second index you will take the number of channels from there, and at last index you will take the number of channels from here. So your output should be 48 comma 64 comma 3. uh, yeah, so I think there are few more things before we start building the neural network or the perceptron. So just bear it with me. I mean these things will come handy whenever you are facing you are training your models, or maybe like if you see that like some errors are occurring. So these might be the most typical errors. Either check for the shape, check for the whether you're doing the permutation correctly, check for the size of the values, whether they match your input dimension. You if they don't, you need to resize everything. So I mean most of the errors, or like you spend good amount of time debugging these things to later realize that like these were the part of the basics. Yeah. Suppose you have two tensors and you want to like combine or concatenate them. So in PyTorch you use torch.cat, and you if you define along which dimension you want to concatenate, it will concatenate along that dimension. So there are two. If you either concatenate along the zero dimension, this is like one below another, or the one dimension, that is like in the column wise concatenation. So zero is row wise concatenation. So if you say the cat rows, it comes out to be this in this manner. So you have so the original size was 3 comma 4. So if you do row concatenation, it becomes 6 comma 4. If you do column concatenation, it becomes 3 comma 8. Similarly, you can actually do manipulate the type of object you have initialized. Suppose you want your like the tensor to be int, you just say that int of a. It will convert the floating point objects into the int. So by default, the whatever the values are initialized in the torch tensor, these are the float point operations. But you can actually use numpy, or not like numpy, but like you can actually convert them into int variables. Now let's move to GPU. So by default, if you run it, if you open a Colab notebook, it will be based on CPU. And but if you want to run these deep learning based architectures, you might want to switch to GPU. So in order to do that, just go to runtime, change runtime, and just click T for GPU, and then save. That will reconnect everything, right? And then we might be able to use it. So it is connected. I'll just so it essentially restarts whenever you are you change the runtime. So you might want to import your dependencies again. So if you say that toss.cuda is available, if it is true, right? So then basically uh, you have the code which is required to transfer your tensors to GPU. So CUDA is a bridge between your hardware and the software, or the tensors you have initialized. Yeah. So there are two ways to initialize a tensor to a GPU. So what you do is like either initialize a random tensor and say there's an option called device. And just say that what is the devices. So in set device, what we are getting here is device is equal to CUDA if CUDA is available, else it is CPU. So if your system has a GPU, it will automatically return CUDA, right? So you can actually directly assign a value to a tensor to a CUDA, or what you can do is like you can assign initialize a normal tensor and then use two function which basically can push it to CUDA, so or GPU. So what you say, let's say the two bracket device. So device here is basically CUDA. But one thing you need to actually take care of is like if one of the value is in CPU and the other one is in GPU, then if you're doing some sort of addition or some operation, then it throws an error. So both the values should be on the same device. So suppose you have a X which is on CPU, you can actually add it with Y which is basically on the CPU, and then you can basically convert that Y into CUDA or GPU, and then do operation with Z, right? But if you do operation with X, Y and Z before without converting it to CUDA, then it becomes error. So let's get started with multi-layer perceptron. So suppose this is a toy example data we have created. So X is basically you have 100 samples. There are total of 100 samples, and then there are two classes, right? And we have equally divided each sample, so 50-50 for each class. And if you actually visualize it, it turns out to be in this manner, right? So there are class 0 is blue, there's class 1 which is orange, right? Similarly Similarly, you have different values. So for even for training, if you visualize, it will be two classes, and uh, the data looks linearly separable. So we can actually try to see if the multi-layer, so like even the single perceptron will be able to predict. So for a perceptron, what should be? We are basically for an input, we are initializing some weights, and we compute a dot product between the x and weights and add a bias term, right? And we are basically using a sigmoid kind of operator where the output, if it is greater than 0, then we say it's suppose it's 1, otherwise it's 0. Yeah. And for loss, what we have done is like we are basically computing the difference between prediction and Y, right? And how do you train it? So for every prediction, you try to update the weight. So your backward pass is basically you compute the loss and you update the weight with a factor that is multiply with the gradient of your uh, loss loss function, right? So you simply multiply with error your input, and then update the weights, and similarly you update the biases. Let us see if we can train it. Right. So we have trained it for 5 epochs. The weight which we have got is like 1.27, 3.14, and if you actually try to do the prediction, it becomes, for the training set it gives 100% accuracy, and on the test set it becomes 93% of the accuracy. And if you try to visualize it on the training set, this is the linear separator we are learning. On the test set, this is the linear separator we are learning, but uh, since it's only a single layer, single perceptron, we are basically able to learn a linear decision boundary. We can actually increase the complexity of the model to learn a non-linear decision boundaries. In that case, your decision boundary looks like this. So that actually can improve the accuracy. Right. Similarly, what we can do is, like, whatever we have seen above was MLP implementation using NumPy. Similarly, you can actually do the same implementation in the PyTorch. Only thing that changes here is, instead of np dot like dot product, we are doing dot mm, that is matrix multiplication, and just you can simply add the bias term here. You'll get the same weights, you'll get the same accuracy. Only thing is, you can actually see improvement in the speed. So next is basically we are actually checking the gradient descent problem. So let us say that you have a function which is sine of x square plus y square, and what you want to compute the gradient with respect of z, and you do it for with respect to x and with respect to y. So what should be the gradient of sine of x square plus y square? So 1 on the out. So what you do is, like, you actually use the chain rule. So gradient of so the derivative of z with respect to x becomes the partial derivatives of g with respect to h, and then h with respect to x. So it can, right? So because like the f is a function of g and h, right? So what you do is, so f here is basically sinusoidal function. So you compute the derivative of sine, it becomes cos, and there is inside term as well, which is x square plus y square, and then you compute the derivative of x square plus y square with respect to x, it becomes 2x, and if you compute the derivative of x square plus y square, it become with respect to y, it become 2y. So your partial derivatives become like cos of x square plus y square 2x, and in this case cos of x square plus y square 2y, and this basically becomes the chain rule, right? So you compute the derivative of f with respect to g, then g with respect to x, right? So this actually is very essential whenever you are trying to train a model. So the back propagation actually takes place using this chain rule only. So if you compute the gradient, it will look like this, where the intensity of arrow actually shows that like what is how steep is the gradient, and the direction basically tells you in which direction you need to move to go to the local minima. Right. So the gradient descent algorithm actually is, so suppose you have a weight w at time step t plus 1. What you do is, like, you'll take the previous weight, that is wt, and update it using the gradient of uh, the function f, which is basically a function of w, and this uh, and like structure is basically the learning rate. So it basically tells you what is the step size with which you are updating the weights, and you do it for all the samples, right? And you do it for all like you do it multiple times till you reach the local minima. or the minima, right? So let's what we do is like we will create a what we'll do is we'll create a simple neural network with basically a perceptron only, but let's see. So you have a x which is incoming. What you do is like there are two parameters w and b, and what you do is like you multiply x with w, so it becomes xw, and add the bias term b. You add the nonlinearity here tan h, right? And then you make some prediction. You make a prediction of y hat, and you compute the difference between y hat and y, what is the your predicted value and what is your actual value or the target value should be, and this the square of this law this term actually becomes your loss. This basically called as the mean square error, right? So let what we have done here is we have initialized values of parameters. We have created a simple graph that is torch of 10h x into w plus bias, and it is making some prediction. For loss, what you are getting is loss is basically y true, which is what it should predict, what it is predicting, and we are kind of squaring both of them, right? And let us see what should we get. We are getting for a value x is equal to 1, I'm getting the prediction should be 0. So why I'm getting prediction 0? So if x is equal to 1 and y w is basically minus 0.5, so xw, so the xw become minus 0.5, bias is 0.5, right? So your product actually becomes 0, and then you do the activation, the product, so the output becomes 0. And what is the true value which you supposed to predict? You were supposed to predict y is equal to 7, right? And your loss become basically the square of your true value, that is 49, right? So this is basically the forward pass of your graph. And now we will see that like how do we actually do the backward pass. So this is called as the like this is called as the back propagation. Yeah, suppose you have two values a and b, right? So whenever you're like initializing this tensor, if you say the require grad equal to true, right? So that means you're like you are creating a graph, and the node a will be a node of that graph, right? And require grad equal to true means like the grade it this like variable actually will have some gradient, right? So like what I've done is like I've initialized both tensor a and b with required gradient, and if I say that c is equal to a plus b, right? Then if I just say the c dot gradient function, it predicts add backward 0. So the new node which I have added, that is c, it's dependent on a and b, and c also requires becomes like assigned in a way that uh, it is basically like will get updated based on the gradient. So the gradient will flow through c to a or c to b, right? So I don't need to assign like c dot require gradient is equal to 2, since a and b both say that like the gradient requirement is true, it c also requires gradient. Yeah, so similarly, suppose you want to compute the loss like the gradient of the loss with respect to w. What you do here is this is our function, like this is our graph. So what you do is like we compute the gradient of loss, and then there's one term which is 10h, right? So you compute the gradient of 10h with respect to w. So and you are basically like hopping from output to input, right? So that is the backprop. So what you do here is you first thing is there's a mean squared error, right? So it yt minus yp is basically your prediction, whole square was your true loss, right? So if you compute loss with respect to w, you compute the derivative of your mean squared error, it becomes 2 times yt minus yp, right? Then there is a tan h term. So tan h term, we have seen that what is the derivative of tan h, right? It becomes 1 minus tan h. So tan h is basically predicting your yp, so it becomes 1 minus yp whole square, right? Yp square. And your yp is basically so input to tan h is basically dependent on x w plus b, and if you are basically differentiating with respect to w, then I think it becomes uh, there's a product term which comes out to be x. Let me just show it to you, otherwise I don't think you'll understand. Might have to switch to iPad. Just a minute. Mm, So this is the graph, right? X. This is the multiplication operator. This is your parameters. So for forward pass, what is happening here? Hmm. So suppose this is, let's say this is the intermediate variable we have defined, this is z. So z actually becomes equal to wx plus b, right? Then this is, let's say this becomes yp. So yp is basically 10h of z, and loss actually becomes yt minus yp and whole square. This is the loss, right? So when you are actually computing back propagation, backward pass, so what you need to compute, we want to compute the gradient of loss with respect to w. So that is yt minus yp whole square. And now I can actually use chain rule here. So yt minus yp is basically so sorry yt loss with respect to yp, then yp with respect to z, then yz with respect to w. So this is the chain rule. Right, so d by dw actually becomes 2 time yt minus yp. Then this term is basically yt minus upon divide, like derivated by z is basically 1 minus 10h, 10h, because yp is basically 10h of z, right? 1 minus 10h whole square z, and then this is basically by dw is basically derivative of xw plus b, that is equal to x. So dx by dw is equal to x, yp is equal to 10, that is 1 minus 10h whole square z, right? And this is essentially 1 minus yp whole square, and then you have the first term, which is gradient of, sorry, with respect to y is basically 2 time y minus y hat, or yp or yt here, right? If you just place everything into place, it becomes this. So the loss term actually become this one, right? Similarly, in term of bias, everything remains same. Only thing that changes here is basically d by dp plus b, that becomes 1, right? So if you want to see what is the bias term for loss with respect to bias is 2 yt minus yp whole square, 1 minus yp whole square, and this is 1, where we were multiplying x, right? Makes sense? That's how we are actually computing the gradient of loss with respect to the input, that is w in this case. So for both the parameters we are computing what is the effect or what change I am making in the output if I change w. So this becomes the gradient computation, and then like whatever the stochastic gradient descent or whatever the optimization algorithm we use that to update our weights. So let me just share this instead. Right, this is the equation. I hope you can see my screen. This is the equation we have derived, and this is what we will be using further, right? So this is what like we are using. So your gradient actually becomes like this is the amount we will be updating your weights. And if you can check like using, if we were actually using that graph, so the gradient actually becomes if you check for derivative with this dot, if you check for what is the dimension, it becomes like, so you can actually use dot grad, right? Like to check what is the gradient, if you like manually compute it or using like use PyTorch to compute it. So like suppose you have a function square loss and you say dot backward, it automatically compute gradients uh, like with respect to that function, right? And if you want, you can actually use simple graph dot w dot grad, and it will show you what is the gradient of w with respect to the loss function, right? So like instead of what do you say, like computing everything manually, so PyTorch actually makes life very easy for us. So simple dot backward function actually does all the gradient computation for us. Let me just, let's see if we can actually train a neural network now, right? So we have created a sample data for you. This is basically data points which are sampled from sinusoidal function, and what we are trying to do is like we are trying to create a like a single layer, but it has like many 512 neurons, and see if we can actually simulate or like understand what the data distribution is, right? So this is our neural network where you have input features is basically one dimension. You are mapping it to 512 dimensions. You have 512 neurons, and then again mapping it to one, which is because the output is one. And for this, like we have means, we are using mean square error, whatever we have just saw above. And for optimization part, we are using a stochastic gradient descent. You have moment, you can actually define the learning rate and the momentum as well. So if you, so like what people generally do, you have a network, you take input, you do predictions, there is a loss function, right? You compute the loss between the predicted and the target. Based on the loss, you do loss dot backward, it compute all the gradients. SGD optimizer dot step is the point where you update your weights or the parameters based on whatever the gradient you have calculated. So this is overall training process. So like if you see that like the original is the blue, the teal colored are the original data points. uh, Red one is basically whatever the prediction we are making, and if you can see on the right, this is the training loss, so the training loss is reducing. Similarly, let's see if we can actually build something for image classification problem. So uh, this is the MNH data set, right? So so this was one of the first data set which was uh, released, and it's basically for handwriting recognition problem, where you have people have written multiple characters and you have assigned like you have a label corresponding to that, and what you want is like for each image you want to predict what is like the like what is written, what number it is. So you have this image of 0 and you have the label 0 here. What we can do here is we can create a simple neural network, and since there are multiple classes, we'll use the softmax function in the output, right? So this is our architecture. What I've done is like I've just used like what do you say, I just flatten out every image into a vector and pass it to a neural network, and it's predicting like out of 10 classes what is the most likely class. And using negative log likelihood, um, right? And this is basically like what are the parameters, like what were the parameters before the update, and then you see that like what are the parameters, how does the parameter change after the update. So you do at least one pass. So you, what you do is like you take like whatever the loss is dot backward, it compute all the gradient, and then you take the optimizer dot step, it updates your parameters or the weights. Similarly, like there are few surfaces which become very tricky. So there is a line of work which actually look into what type of optimizer works well. So the rule of thumb is whenever you are starting a new problem, so just start with Adam. It works best for most of the cases. So suppose like there are multiple very steep local minimas, right? So if you are stuck in one of them, you'll just be stuck around them. So like I think in most of the cases, whenever I start with building a problem, I simply um, start with like what do you say, Adam. And what is the typical learning rate I try with? 1e minus 3 is something which I use for whenever I'm actually building my first like baseline, something like that. So I think this notebook is basically will be available to you. Just see if you can actually run it and understand what's happening under the hood, uh, and hopefully will appreciate like how the PyTorch actually makes life easy for us. Let me just. So like I just want to show you like the previous thing was like informative but not very well structured. So what like I generally do is like I structure my code in a very modular manner. So like there are, so I think these are the maybe the best practices for like maybe training the architecture the models. So I generally split my like code into three parts. So first one is the your data loader, where everything related to loading data, pre-processing should be done in that part. The second part should be your model architecture. If you're defining whatever layers you're defining, should be done in that part. The third part is basically your optimization and training loop, right? So these there are these three part. I like completely segregate everything, and I try to make like maybe functions or like see whatever is the easily available. So let me just show. So what I generally do is I define it. Suppose there's some segmentation data I have to take. I define it as a class segmentation data set. I initialize whatever the variables are, right? And like this image name, you since you have loaded all the image from os.list directory are there, so I iterate over all of them one by one and pass, and this return just return it to my data loader. So what you do is like for an image, I just load this image, segmentation mask, opens it, and if I have to do some sort of like maybe transformation like resizing or maybe some sort of augmentation, I'll do it here and then return my image and the mask here, right? And this is like I just say data set is equal to segmentation data set. And what data loader does it like it calls this function, uh, this get item multiple time function, and create a batch of 4 images, right? And it shuffles those images also, right? And it passes on this to my inside my training loop, like so the output will become 4 comma 3 comma 256 comma 256, and your mask is basically 4 comma 1 comma 256 cross 256. So this becomes your your image dimension and the output dimension. This is the mask. So generally I structure everything into in this manner. For MLP architecture, I define it as a class. You define different what are the different layers. Maybe layer one, say let's say nn dot linear. It's a linear layer. MLP, you have input size, output size, like Can you see now? Okay, I might have to reiterate just quickly, sorry. So this is the class actually I defined. So there are three parts. You have initialize all the variables, right? And this get item function basically loads all the value and feed it to your data loader. So this is your data loader, right? Which takes uh, it loads value, it feed values in a batch size of 4 to your training loop. So if you say just iterate over your data loader and check for the shape of the images and the mask, it says that 4 comma 3 comma 256 comma 256, and the mask size is like 1 4 comma 1 comma whatever the dimension is. So the 4 is basically the batch size. So whenever I'm training, I make shuffle is equal to true. Whenever either I'm testing or during the validation phase, so that like there is no stochasticity, I make shuffle is equal to false. So shuffle actually helps. So whenever you're training, just try shuffling the order of the image in order in which the images are loaded, so that like model does not memorize everything, right? So this is the way I structure my data loader part. This is the part, this is self dot transform, which what it does is like it, if you have some sort of a resizing, right, or normalizing to do, it basically does this. So all the augmentations will come here inside this function, is this if call, right? So you load images, you define path, load images. If you have any augmentation, do it here, return image or mask, or maybe whatever. So suppose you have a text information, you just return image comma text, right? And your data loader take care of that. Like it calls this function and then just process everything in a chunk of 4, and this we can actually feed it to MLP. This is my like how does I like assign or like define a MLP or any architecture. So you have a class, you define what are the different layers you want to use. Suppose you have f1, f2, f3, right? So nn dot linear basically has an input, we have an input size and the output. So like suppose you are we are training for like MNS dataset, so the input will be 784 dimensional and the output can be anything, right? Like it depends on what kind of architecture you're building. This is where you define or initialize your like layers, and def dot forward is where you call them. So how do I call them? X is equal to f dot relu uh, self dot f1. So x, so whatever the input is coming, I'll just pass it to fc1 fully connected layer 1, and then apply a non-linearity on top of that. So this basically returns me the first like output of first layer. Then again I'll just pass it to the second layer, cell.fc2, apply a non-linearity, and then it returns me the x. Then same goes for the fully connected layer 3, right? uh, uh, right? And if you actually look at the graph, so it looks like this. So you have weights for weight and bias for fully connected layer 1, you have weight and biases for fully connected layer 2, like, and then again you have fc3, you accumulate everything and then it predicts something. This was for a classification problem where output size, suppose we were basically building for MNS, then output size is 10, which is basically depend on number of labels we have, right? So but in case of maybe sinusoidal data which we are seeing, right, if you want to predict what is the next value for that, you we term it as the regression problem, where the output is single like neuron. So output size here is 1. So for the classification problem, the output size is basically depends on number of like labels we want to cater to. So like let's say you have the linear layer, you have, it will basically, if you say summary of model, it will give you all the number of parameters. So the total number of parameters we are using is 118k, right? And all of them are trainable. So in some cases we use pre-trained model as well, like ResNet and those things. Then not all of them we want to like touch, right? So you want to like use ResNet to extract out features. You just want to build another layer on top of ResNet and just train that. So if you want to do that, like, then your number of trainable parameter will be only the layer you have put, and the non-trainable parameter will be the parameters for ResNet. Right, and in mm, let me just see. Then the training loops look like this. You initialize the model, you define the whatever the loss. I generally use criteria is equal to whatever the cross entropy loss, if you're using for, if you're training it for multi-class classification problem. Then I generally try with optimizer as Adam, where it takes model dot parameters as one of the input, and then you define the learning rate. So you define what the number of epochs you want to train it to, and you iterate it over all the whole batch, right? uh, for uh, for batch id, your data and target from data loader, right? And if, because the incoming, what you do is like you put your model to gpu, your data which is incoming is in cpu. So what you need to do is like you place everything into one space. Either you put model into cpu, or like you put, or the better way is like you put your data to gpu. So this 2 is basically shifting my data to gpu. So and then what you do is like I feed model data and predict something, which is the output. I compute the loss between my prediction and what is my target, right? So right, then loss dot backward actually compute all the gradients for that neural network, and optimizer or step basically update those weights with whatever the learning rate we have chosen. So if the learning rate is too high, the updates will be very fast. However, like it might not converge to a good solution, because it will be fluctuating a lot after a while. So people generally use scheduling, like initially when you're training a model, your learning rate can be high, you'll take much bigger steps, but when you are close to minima, you take lower steps, smaller steps. Similarly, you have a test loop as well, where in this case, in the test loop, you say just toss dot no grad, where you don't need to compute the gradient, right? uh, you don't need to compute the gradient, and you just see that like what is the maximum probability of which you're at what index you're predicting, uh, in what label basically you're assigning the maximum probability. Suppose you have given an image of 0, and at the 0th index basically you're predicting it has the highest probability. You just take max of it and then assign it to a class label. So that's how you move from basically the probability to a label space. And then whatever metric you want, you can compute. So I think we will discuss them maybe in the next sessions. How do you actually evaluate the model? What are the best practices for training? What are the different metrics you use? What are the different loss functions? But just to show you the overall structure, how does like how to basically write or like structure your first code. I think this is what should be the takeaway. So make it clean. So just have a separate segment, data loader part. Have a separate model architecture. Have a separate training loop, so that you know that like where you need to modify things. With PyTorch, things become very simple. Like you don't need to take care of the gradient computation, or the even the like grade parameter update, weight updates. Only thing is you need to be very sure that like you're feeding the correct data. Your architecture is basically correct. You're not like learning any shortcuts or some anything, and you're training on the whole data. And your loss is basically accumulation of whole batch, right? And generally you save the best model based on your validation loss. So you train, you compute loss for the training data, you compute loss for the validation of the dev set, and then what you do is like you save the best model once you are done with the training. So I think in the next session we'll see that like how do you actually train. Maybe we extend MLP to CNNs, right? And like what are the common architectures, maybe ResNet, LXNet. Like we can actually see that like if we suppose build it from scratch, how does it look like? How do you actually use the pre-trained architectures? But yeah, everything for the next session. Uh, yeah, I think this is what I have for today. If you guys have any doubt, like just let me know. Maybe in comment section, or now also is a good time. We have some time. If you don't have any doubt, let's close it here. You can actually post your doubts in the discussion like channel we have. I'll see if we can if you want anything to be added to the sessions, like we can actually just put your comments there as well. uh, just say if anything is not working maybe, or you want to add maybe a more coding sessions or more theoretical part, whatever it is, just let us know. We'll try to incorporate them. So I'll close it here. Thanks everyone for joining. Yeah, have a good weekend. Bye.